And then here's John with how we compile for Carbon. Go ahead and take it away, John. Thanks.
So hi all, I'm John. I've been working on Carbon for a few years now, and I wanted to talk today a little about the current status of Carbon, but mostly just to give a deep dive into how the compiler works so that everybody maybe understands a little better how things fit together. I do want to note, I'm hoping to use this recording for public use and put it on YouTube. So if you have any Google confidential questions, please hold them to the very end. What I'll be talking about today, though, is the status, how the compiler works at a high level, and then talking a little more deeply about Parse, the Semantic IR, and constants and type coherency within Carbon, followed by that two-part Q&A. So to start off with the status, right now Carbon can compile simple binaries. If you go on to Compiler Explorer, you can see some of this. You can also check out the examples on GitHub. Within Carbon itself, a lot of basics are working. We do have checked generics, which is one of the more interesting features we feel largely working. Templated generics, more similar to C++, are still at a proof of concept level. More recently, too, we've been getting C++ in ROP. This has mainly been contributed by Boaz and Ivana of the Munich office. The current level there is that you can use non-overloaded functions that take in primitive types. Looking at the rest of the year, we want to keep expanding that in ROP. So more functions, more types, classes, not quite templates yet. That's still a little more work. But we do want to prioritize the necessary Carbon language features that are going to help support C++ in ROP. So we still have work to do on things like destructors and choice types for enums that we just need to keep working on. The other big thing we want to work on is the memory safety model. We have been holding off on this for a bit because it relates to the generics model within Carbon. And now that generics has progressed better, now we're going to work on memory safety. Looking ahead to next year, what you can expect is we're going to begin more seriously evaluating Carbon and Google's level of interest in it. To answer the question whether Carbon is interesting enough, we'll probably need an actual MVP at that point. And we may want to start merging into LLVM integrates to ease in evaluation of Carbon. In order to get or as part of this too, like we expect to keep building out C++ in ROP. So right now we have Carbon calling C++ code. This is more when we'll be talking about C++ calling Carbon code. Another big thing here is template support. Will probably be at a point where we can start building out basic templated types. The other big thing is if we are designing memory safety this year, then 2026 would be when we're implementing it. So I want to emphasize finally, Carbon is still an experiment. We hope to figure out whether we can end that, but that's more of a next year thing. So that's about it for status. Most of this presentation is really going to be about how the compiler works. And to start, I'll give you an overview versus Clang. So if we're talking about compiler models, both are LLVM front ends, and this means both are ending up at LLVM IR. If you talk about phases, though, Clang has an interleaved phase model where Lex, Parse, and semantic analysis all sort of occur together. In Carbon, we have distinct phases. So we Lex the whole file, then we parse the whole file, then we check the whole file. The outputs are similarly a little different. So in Clang, the AST is produced. This is nominally an abstract syntax tree. It's kind of actually a syntax and semantics graph. In Carbon, Parse produces a parse tree, which is a concrete syntax tree. That means it only includes structure, no semantics. And there's also the semantic SemIR or Semantic IR. In Clang, the cogen AST walk emits non-SSA LLVMIR. There's just a few extra instructions there to guarantee things are correct. In Carbon, we model a bit more about how the LLVMIR will work. So we're able to emit SSA LLVMIR. So these are both sharing the LLVM backend. And at Google, we talk a lot about coding ecosystems, like how Java and Kotlin are both part of the JVM ecosystem. You can think of Carbon and Clang as both part of the LLVM ecosystem, or C++ ecosystem, if you will. This is building on all of the investment Google's made over the years on Clang and LLVM. That's going to continue. We don't want a C++ compiler for Carbon that's different from Clang. The real benefit, though, of using Clang is that we can interop within the LLVMIR. So if we are inlining a templated C++ function, we can have Clang emit the LLVMIR for Carbon and use that pretty directly. This is also similar to the relationship with Rust. So Crubit is using Clang for C++ interop, Swift as well, and Carbon may also add an interop with Rust, still using the LLVM ecosystem bit. So I just want to emphasize, like, this is all fitting together in one big LLVM group. That said, to talk about compiler phase differences, so C++ requires interleaving. That's not really a choice Clang could have made differently. Parsing C++ code depends on semantic analysis of earlier code. If you think about something like A less than B greater than C, that could actually be a templated variable instead of two operators. Carbon avoids this. We just provide two different a context-free grammar. There are two different syntaxes for that sort of construct, and that flows through the entire language. That said, distinct phases are still a choice. We could interleave, but we think it's better to break these apart. That's because now we can debug with the output from each phase. We can just Lexa pretty easily. We can just parse really easily and see the distinctions between each. Tools can also pick and choose which phases they want. So for example, a formatter only really needs parse. And our parsing is super fast, so that means formatting can be super fast without building a separate tool like Clang Format did. The other aspect here, maybe more subtle, is that we think this can give us better cache performance by reading and writing each section of data at a time. So for example, our first phase is Lex. This is just tokenizing source code. It does a simple classification of tokens. It can distinguish between keywords and identifiers. It does also do pairing of brackets, and it'll detect missing brackets and do a simple recovery. If you're missing a curly brace, it tries inserting a curly brace at a reasonable spot. The output of Lex is just an array of tokens. We do a lot of packing in Carbon, in Carbon. Tokens are 8 bytes each. We do have some trade-offs here, so we limit ourselves to 8 million tokens. If you think about source files, though, this probably means something like a 40 meg source file. You can reach that with generated code. Probably no human is ever going to write it. And if some generated code hits it, probably there are ways to refactor. Like they can just split that in two, and that'll probably be enough. The other thing I'll note here is the tokens do include the full source location versus versus Clang, which separates that out, I believe, to a separate structure. And at the bottom here, I have an example token. Again, it's the kind, line, column, etc. All of this is fitting into just the 8 bytes. Given the tokens, now we can create the parse tree. And here's a simple parse tree for y plus 1. I'll dig into this more later in the presentation. Right now, I just want to highlight 2 things here. So the first is that we can tell from the parse tree, var is declaring x, and we know that because colon is a binding pattern. This is part of how Carbon declares variables. And I want to contrast that with y. So we know y is an identifier. We don't know if y is valid or what it is. This is just contrasting with Clang's AST, which would at this point already know whether y is valid, what its type is, and so on. So the parse tree is feeding into our SemIR, which is Carbon semantics. And this does include instructions for desugaring. And this is really the best comparison for Clang's AST. It has pretty much all of the information available to it. As an example of the SemIR, just very briefly, a little code, x equals 1, can become a lot of IR. But again, a lot of this is just desugaring. So we have x.var declaring the thing, we have the literal 1, it's assigned, and then we add x for name lookup. When you lower this, it is going down to LLVMIR, all that desugaring just vanishes. And so we have these 2 IR instructions, declaring a lifetime and storing a value into it. What I want to just summarize this as, we do have distinct steps, but it is the same goal as Clang in that we are trying to generate LLVM IR. So digging back into that parse phase, parse in Carbon is an iterative stack-based state machine. And I do want to note iterative. All of Carbon is iterative. I know Clang does a lot of recursion. Some of our engineers feel a little burned by stack frame issues in Clang and how occasionally a new stack recursion pops up and becomes a problem. So we are going iterative from the start. Within the state machine, though, each state is looking at the token cursor back into that output of Lex to decide how to progress. And tokens cause state changes. They can create nested states within this stack. For example, var will push states to both process the pattern, which is going to be x:(i32, and process what's after the pattern, which it'll determine when it reaches that point. Again, that's because the token cursor has not reached that future point. We are not doing look ahead. The output is always a structurally valid tree. We have certain details to parse which define what structurally valid is, and we do insert error recovery nodes to reach that state. But the structure is well known. And the other thing I want to highlight here is that this is pretty much just as fast as Lex is. It's not doing too much additional work. So the speed is pretty much the same if you're parsing versus Lexing. So to talk about this parse tree in a bit more depth, I show you this tree structure, and you may think that's pointers, but we use indices in Carbon a lot, not pointers. This is actually an array, in particular a post-order array. So here's a different representation we typically use. We do indentation here to make it easier to read what the actual array structure is, but this is just a list of nodes. And to really describe a couple nodes, I'll talk about the first and last here, the variable introducer and the semicolon. So there are just a few parts here. There's the node kind. This is just an enum value. The text of the node is actually just an index back to the original token, and the token knows its text, so we can get that indirectly. And then there's the subtree size. So because this is just an array, we need some way to figure out what the subtrees are, and this is inferred actually from the node kind. It's not actually stored. Some node kinds have a fixed number of children. So for example, if this were a binary operator, like a binary operator always has 2 children. I chose to give these 2 particular nodes as an example because introducer is bracketing the decal node. And so the subtree size of 10 here is just because we can traverse the subtree and find where its matching introducer was. Because there's so little data here, we can pack everything into 4 bytes, which again is another nice little array. When we're talking about using it though, I showed you this, but it's actually a lot of just formatting. Again, the subtree size is implicit. So this is really the information there, just the kind and the token information. And if you want a different view of this, you can also think of this as an IR. It's really close. Like we already know the subtrees, we can treat previous nodes as inputs to later nodes. And this is actually a bit how checking works in Carbon. This is an IR with linear execution. Like basically checking is a linear parse tree walk. So with that brings us to the semantic IR. So in semantic IR, we have a single instruction. Like I just want to get into the detail of what's shown here because I'll be showing this a lot. So the first element is just the name of the instruction. It's a name of a result. It can be disambiguated by a source location like .loc3 there. And, I32 as a name comes from, we used an I32 type literal to create this. Then we have the type of the result. So type here is actually the type. It's not just a placeholder. It's the type of all types. We can also have an expression category here. This particular instruction does not have one, but we could also have an initializing instruction or a reference instruction. That's just part of how we generate IR later. Then we have an instruction name. So this is a class type. We have at most 2 operands. This is just an arbitrary number. It helps us pack instructions into storage. And then we have this constant value, which I'll dig into a little more later. Just know it's there. And if it were non-constant, nothing would be shown. With these instructions, we then form blocks. A block, as we think of it, is just a sequence of instructions. The intent here is that it's flexible and multi-purpose. So for example, the same concept of an instruction block could be an entity body, whether a function body or a class body, could be arguments or parameters, tuple declaration. We have separate blocks for flow control. A series of instructions might be spliced in from another block if we aren't sure how many we need later, like if there's a slight ordering issue in the creation. And also imports are another kind of instruction block. So this is just a handy tool to store data, to store a set of instructions. And for how this fits into the core checking, so I already described the parse tree. As we process the parse tree, we push them onto push the processed nodes onto our node stack. This is associating nodes with an optional ID, often an instruction ID, sometimes some other kind of ID. It is decided by the node kind, though. And then we also have SemIR being printed by checking to a current instruction block. And again, this instruction block can be many different forms. All we need to know is that it is a block. The block cursor is moved around as part of scope changes, just as an example. So I've tried to describe the concepts here. Let me try and show you how this is actually working in action with, again, x equals y plus 1. So at the top, I have sort of the parse tree ordering of this. So you'll note a couple things get swapped here, like it's x I32 colon instead of x colon I32. Also, I have this little star node here. We have little virtual nodes we insert because of it wanting to transmit extra information from parse to SemIR in order to get things to execute correctly. And this star here is in particular noting that we are really at the end of a pattern versus in a nested pattern. And then we have equals y1 plus, again, switching the order similar to the colon, and then semicolon as the end. And what we'll be producing is this node stack and an instruction block. For processing var, it's very simple. We just record that there was an introducer. We don't have more information yet. For x, we can start doing something a little more interesting, but this is still just an identifier. We don't yet know how it's used. Similarly with I32, we know this is a name of some, or a name reference kind of. This is a type literal in particular, so it does add a type constant. And then you can note the comma percent I32. That is noting that the newly added constant is associated with the node on the stack. So with colon, things get a bit more interesting, and a lot just moved here. So we do pop the identifier and percent I32 as part of processing the two operands to the colon. As we do this, we can create a constant that describes the binding pattern's type. And that is percent x.pat being emitted to the instruction block. That's sort of our way of indicating that we had this binding pattern in evaluation. Then we push the reference to x.pat back onto the node stack. And this is our breadcrumb as we continue parsing. So I noted this star is indicating we're at the end of the pattern. It is, and that's essentially what it's doing here. It pops the x.pat that we just added and wraps it to indicate there is this full variable pattern. In this case, it's pretty much the same. Some cases may be more complex, but I'm giving this simple example. Equals, so some variables may not have initializers. We do need to track that this one does have an initializer. On the right, you'll note another x.var pattern was added. This is so that we have a little more state for later for the assignment. Moving into the expression, we know y here is an identifier name. We do a name lookup for it because this is within an expression context, and we store the result of that name lookup as %y. One is an integer literal. We just form a literal value for it. Plus is another operand. So this is, again, it's a little more work occurring here. It pops the two nodes that were its arguments. It does a lookup for the plus operator, where I have this elided as just there's lots of desugaring there. And then int.sadd is the call to that operator, which we store that result back onto the node stack. Finally, as part of the semicolon, and part of the semicolon, we pop back to the introducer, basically processing everything between. This means we take that initializer value and assign it back to the pattern, and then we can introduce X into the name scope for later use. And you can see that on the bottom right as assign and bind name. In full, it actually looks a lot like this. There are a couple of things I didn't note here, namely this name binding decal and splice block. This is just sort of where I was mentioning we sometimes create instructions a little out of order or have a little extra desugaring. This is how it's represented in the IR. So SemIR is really just semantics, but in an IR form. Finally, I wanted to talk a little about how constants and type coherency work within this model to sort of show how things come together as we go a bit further into the language. So if instructions are really the building block of semantics, constants are the building block for compile time evaluation within Carbon. Every instruction is going to be assigned a constant value after its own construction. The constant value could be runtime, a non-constant value, in which case it's not really constant as you may typically think of it, but we still call this the constant value. Anyways, every constant value is also an instruction. So these are just references back into the same storage in a lot of ways. I previously mentioned there are a few kinds of constants. To get into a little more detail here, we have the non-constant cases, var x, or the result of a function call, or system call in particular in this case. We have symbolic constants, which is essentially how we say there are unresolved generic parameters. For example, t in vector t:(bang) type, that is a generic parameter trying to tell you what the type of the vector or type is stored within the vector. These can be attached to generic entities. They can also be unattached. I won't go into too much detail of what that means, but this is an attached example. We do also have concrete constants. This is probably what you most typically think of when you think of as a constant, because there is nothing generic about them. These are things like 42, a pointer to a type, or a particular instantiated generic type, if you will. And these can be in particular used for compile time evaluation. For example, if you say 2 is a constant value and 4 is a constant value, you can evaluate 2 plus 2 is equal to 4, and that's just all using concrete constants. So digging a bit further, types are constants as well. So again, I32 star is a constant value. This means that constants are also part of type equality within Carbon, where we do canonicalize the constant values, and we can basically do a straight index equality comparison for this. Although I noted the symbolic types, I will note here, generic types are also constant values, so the full class vector with a generic parameter is still a constant value, and meaning we can also have a function that returns a constant. So the type here, as I noted, is the type of all types, so we can have this declare vector function that is returning a type, and we could in theory have this be all constant time evaluated. If it's okay, I'll hand I'll get to questions at the end. So for types within SemIR, every instruction in an evaluated block has a type. They are pretty much everywhere. When I say evaluated block, though, I do primarily mean entity bodies, particularly functions and classes, but also other things. There are just some blocks that we don't have types, and it's a bit nuanced. But most cases you think of have types. This also means many instructions are doing type propagation. Usually it's just a simple propagation. For example, name reference just forwards the type of what it had in it. And so if you do something like type of LHS is equal to type of RHS, again, this is a simple index equality. Like it's just comparing one field on each of these instructions. So regarding how we form these constants, let's talk about first about structural types. So when I say structural type, I mean things like tuples and structs. Tuples you're probably familiar with from like Python and similar. A structural type is not a C++ struct. It is just essentially associating names with each field. Because these are mainly structural, though, the type constant is based on the structure, and this is just a simple hash. This does mean that each copy of that in source code is going to be canonicalized separately. So if you copy a tuple multiple times in source code, each of those is going to be canonicalized. That just means there's an incremental cost when you repeat something. This can be avoided with aliases. Again, aliases propagate the type. Because they are just propagating the type, it means the type does not need to be rehashed. Getting to declared types such as class and interface, but also I'll note FN is a type within Carbon, or declaring a type, so functions are types. Carbon allows up to 3 declarations for any of these. We have the extern declaration, which is different from C++ as extern. I'm just noting this so that you don't get into this mindset that they're the same. We just are reusing the keyword because it has some similarities. So the extern declaration, the forge declaration, and the defining declaration are 3 declarations. And you can just have a definition that could be your only declaration. You could have a for declaration and a defining declaration, but this is just the limit. 1 is the minimum. The first declaration of these is always the owning declaration. So this is in particular one of the differences between declarations in C++ and Carbon is that we do have this concept of a first declaration. Later declarations always have to see that owning declaration so that they know they aren't the first one. And it can see it by either having that other declaration be in the same file, which you might do with a for declaration, or in an imported file, such as, you know, a header versus implementation file. To explain how this relates to imports, so structural types, again, they're just structural, they're hashed. We reevaluate the structure, which, to be clear, does mean more copies of that hash. But it's important because type coherency is then based on the hash according to the current IR. If multiple files declare an equivalent structure, we are just rehashing to the same value in this importing file. For contrast, with the declared types, we actually use the constant of the first declaration. And this is why it's important that redeclarations all see that first declaration. They need to leave breadcrumbs so that anyone importing any of those can find back to the first declaration. And then type coherency of declared types is based on that first declaration. We use that constant value of that first declaration everywhere across all importing IRs. So overall, this gives us a pretty simple model because we have that first declaration to deal with. All of this does mean we can compare types as indices just to figure out whether they're the same. And this does give us good performance, of course, because it's a simple comparison. And there are trade-offs, though, to this, too. Like, the fact we do have to have a first declaration that everything sees it sort of shows how this is shaping the language design in return. We've chosen to limit the number of declarations you can write. And this does also diverge from C++. So in C++, you can forward declare the same entity as many times as you want. And Clang has to figure out that those were all actually declaring the same thing. And this different coherency model will probably give us some complexity within Carbon because we need to all make all of this fit back together at the end of the day. So it's not perfect, but it does give us a lot of benefits within Carbon itself. And this is also, in a way, one of the ways we're trying to step forward with Carbon is by just creating a new language instead of incrementally evolving C++, we're able to take steps like this. So what I really want you to take away from this is that Carbon is pretty different from Clang, but it is still a compiler. It is still just another LLVM front end. It does a lot of different things, but at the end of the day, it's still getting back to the same result. If you're interested in a little more, I didn't delve into generics today, but Richard did give a really good presentation at the LLVM dev meeting, and it's on YouTube if you want to watch that. When Richard is talking about generic substitutions there, those are just more constant replacements. Again, getting to the constant model I described. Also, I didn't talk much about interop with C++ today. I'll probably be talking more later this year about this. Many of you will hopefully be there for that. So thank you for your time. I'm happy to take questions now. Please do focus on non-confidential questions for the moment. Again, I'll give a little more time for Google questions later. Thank you. Eric, I think you popped up a question during the presentation. Did the import stuff answer it?
I did. I was wondering if like the types compare across TUs or if the IR is unifiable in that kind of way to where like I32 star would compare to I32 star no matter what translation units it's in, or if it's more just like a memory address kind of canonicalization.
It's going to yield a different constant value in each IR just because of how the information is tracked. But that is where when it is imported. So I32 star is sort of, I believe it's getting back more at a structural type. Yeah, I think it's more structural because the star is a structural aspect to it. That it is a pointer is structural. So we'll essentially take I32 and generate a constant for that, and then the star for a constant, and generate a constant for that. Since I32 itself is a well-known constant, We do have a single declaration of that we go back to.
Okay. But everything else, like its structural equivalents, basically, at that point, then?
Yeah.
Sweet.
But I will emphasize, though, while it is structural equivalence, if you have like an I32 star mentioned in another IR, that has a constant value. That constant value is imported once per IR and recanonicalized into the current IR, so we know its local constant value. So then, given two different IRs, we're basically figuring out the constant value for the current IR per imported IR. And so if you, in particular, repeat it in an import, it's only pulled in once.
That makes sense. Cool. Will things that are structurally identical but named differently compare differently? Like, say, a struct that has two I32s in it, but is named two different things in two different header files. Will those?
Yes, the names associated in a struct are part of the type information.
Awesome. Cool. Thank you. And if there are no more questions, I will stop recording so John can answer anything else that might come in after. Sweet.